Now you can make a delta x tends to 0 as well as delta t tends to 0. Therefore, you will get a limit. By using the simple calculation, the delta x is this much, where p and dq is equal to half times 1 plus mu times this and 1 minus mu times divided by delta. Now we are using the central limit theorem. Let x1, x2 be a sequence of independent, identically distributed random variables with the finite mean mu and a finite non-zero variance sigma square, and let Sn be a sum of first n random variables, then Sn minus the mean of this random variable divided by the standard deviation of this random variable converges in distribution to the normal distributed random variable with the mean 0, variance 1. So we are going to use this central limit theorem for our random walk scenario. And for large n, the n of t is equal to n, where n is very large, you can conclude the St converges in distribution to the mean of this random variable s of t, that is mu times t, and the variance of this random variable is sigma square t. Whereas here we have used the central limit theorem, the random variable minus their mean divided by the standard deviation converges to the standard normal. But here we are saying the s of t converges to the normally distributed random variable with the mean mu times t and the variance is sigma square t. That is different from this mu and sigma square, where mu is discussed here and the sigma is discussed here. Since t represents the length of the interval of a time during which is the displacement, therefore instead of s of t you can go for s of t minus s of s. Since it is t is the length of the interval, therefore you can go for the s of t minus s of s. That will converges to the normal distribution with the mean mu times t minus s and the variance sigma square times t minus s, where s is less than. The way we discuss the properties of random walk, it has the increments, it has the property of increments are stationary as well as independent. The same logic can be used here. So here the increments s of s minus s of 0 are mutually independent. Increments are independent also. Now we are defining the Brownian motion or Wiener process. A stochastic process is said to be a Wiener process or Brownian motion if it satisfies these three conditions. For t greater than 0, the sample paths of Wt are almost surely continuous functions. For the interval 0 to Tn in this form, for all n, the increments are independent as well as stationary. The increments are independent random variables as well as stationary. And every increment has normal distribution with the mean mu times t minus s and variance sigma square t minus s. This is what we have concluded in the limiting case of normal distribution. The increments is normally distributed with the mean this much and the variance this much. So this is what we have given as the conditions of a stochastic process will be a Wiener process. A Wiener process Wt with the mu of 0 is equal to 0, mu is equal to 0 and sigma square is equal to 1 is called the standard Wiener process. Whenever it is normally distributed with the mean 0 and the variance t minus s, that means the sigma square will be treated as 1 and the mu will be treated as 0, and also w0 is equal to 0, then it is a standard Brownian motion or standard Wiener process. So any stochastic process satisfying these three conditions will be a Wiener process or Brownian motion. The sample path of Wiener process, it looks like this. By definition, Wt plus S minus Wt, that is the increment, follows normal distribution. It can take a positive and negative values. The sample path of Wt is a continuous. There is no jumps. And the limiting case of a random walk will be the Brownian motion. That also one can visualize in the sample path of Brownian motion. Now we are going to discuss a few important properties of a Brownian motion. The first important property is a nowhere differential. You can see the sample path of a Brownian motion. If you see the sample path of the Brownian motion, it is a continuous function, but it has too many fluctuations at every point. So this is a one sample path. So the first property says the sample path is not differentiable anywhere, or it is a nowhere differential. It is not possible to define a tangent line at any point in the sample. You can see it in the sample path figure also. Using second order moment convergence of random variable, we find the limit delta t tends to 0, the variance of the difference of this random variable divided by delta t. If you find out this limit, if this limit is a finite, then we can conclude it is differentiable at the point t0. Suppose you have a real valued function f of x, and if you want to conclude the real valued function f of x has a derivative at the point x0, then you should find out limit delta t tends to 0, f of t0 plus delta t minus f of t0 divided by delta t. If this limit is a finite, then you can conclude the real valued function f as a limit at t0. Since the w's are the random variables, and we know the mean and variance and also the distribution, and the difference is going to be a random variable. As a delta t tends to 0, it is going to be we should find out the convergence of this difference of random variable divided by delta. So one can use any mode of convergence to conclude, to find out the limit delta t tends to 0 of this quantity. But here we are using the second order moment convergence. Therefore, we are finding limit delta t tends to 0, variance of this random variable. The difference is a random variable, difference divided by delta t is a random variable. So we are finding what is the convergence of the function of random variable via second order moment of convergence. So if you find out this quantity, since this difference has a normal distribution with the mean 0 and the variance delta t, therefore the variance delta t has to be treated as a constant. So the variance of 1 divided by constant times this will be 1 divided by delta t whole square, and the variance of the difference of this random variable is delta t. Therefore you will get infinity as a delta t tends to 0. Since this limit is equal to infinity, we conclude the sample path is not differentiable at t0, Since T0 is an arbitrary time point, therefore it is nowhere differentiable, or it is the sample path is not differentiable at every point, every time. The second important property, that is a strict and stationary increment. We are not saying the given stochastic process Brownian motion is a strict and stationary. Here we are saying the increments are strict and stationary. The increments are strict and stationary. That means the increments are satisfying the time invariant property. The strict and stationary means it has the time invariant property in the distribution. So for that we are finding the covariance function. You know the definition of covariance. So covariance of s comma t, it is lambda, it is going to be s. The covariance of s comma t is equal to minimum of s comma t, because here we have concluded for s is less than t, it is s. If you make it t is less than or equal to s, we will get t. Hence c of s comma t is minimum of s comma t. Therefore linear process is not wide and stationary, whereas we can conclude it is a strict and stationary increments. That means first you find out the increments, then one can prove for any finite dimensional the joint distribution is same as the joint distribution by shifting the time scale h. For every h, the increments satisfying the condition the joint distribution are same the original joint distribution as well as the incremented by h. Therefore it is going to be a strict and stationary. And using the covariance function, we are concluding it is not a wide and stationary.